Hey everybody, I'm Chili. Welcome back to Intermediate C++ Tutorial 8. Today we're talking about std vector. Vector is going to revolutionize our C++ code. It's basically a container that acts like an array, only it's dynamically sized, resizable at runtime, and it can hold any data type you want. Basically, it's our dynamic int array on steroids and meth. In this video, I'm going to introduce the basics on how to use vector. I'm going to talk about how vector is implemented under the hood, and I'm going to talk about some performance/efficiency issues and techniques. All right, so we'll start off with an empty project. We got our int main here. Let's include vector. Now, vector is a dynamic container, so we can determine its size at runtime. So let's do something that takes advantage of that. We're going to include IO stream. We're going to prompt the user for input and store that in int size. Then we're going to use that to create our vector. Creating a vector, super simple, std vector. Now, vector is a template class, which means that we can specify something about it. Specifically, we can specify the type of data that it stores. We can have vectors that store any data type that we like. So we're going to make our vector store ints. So we do angle braces int, and we give it a name, vec1, and we call the constructor with the parameter of an int, and that will allow us to specify the size when we create it. It's going to default the values inside of that vector to whatever they normally default to. Now let's print out the contents of that vector. We're going to loop from int I is equal to 0 to size, and we're going to use that value I as an index into our vector container. So as you can see here, we can use the square brackets and an integer value to index and select elements in the vector, just like you can do with a standard C array, just like you could do with our dynamic int array. Finally, we're going to pause the program, wait for the user to hit enter. So when we run this bullshit, what do we get? How many? Well, I mean, let's go for 12. And your vector contains 0, 0, 0, 0, 0, 0, 0. So whatever we're doing right now, it seems to be setting all the values to 0 by default. Now we can control our loop with the size that we got from the user, but we could also use the size of the vector directly. So we could go vec1.size, and that will give us the number of elements in the vector. We could also loop like this, but there is an even sexier way to loop, because vectors, you can use range-based for loop in a vector. So I could just do, for each, const int n in vec1, and then I could just output n like this, and this will motherfucking work. Pretty sweet. Range-based for loop works with your motherfucking vectors. Now in the constructor, we can also specify a value that it will initialize all members to when we create it. So we could go, give us a vector of all 69s. And we run that and we say how many? Well, I guess I want 69 of them, don't I? And there you go. You got it, bro. So you can give it a default to initialize all the values to. You can also give a list of specific values to initialize this guy to. So you can go vec1 is equal to, and you do your curly braces, and let's put some classics in here. 69, 420. Let's see if we can put a variable in there as well, size, and we'll run that. Let's put 10. 10 is good, and there you go. 69, 420, 10. Beautiful. Now, with the exception of being able to use the initializer list and, being able to use range-based for loops, vector probably looks quite similar to our dynamic int array, but there is so much more going on with vector. And before we get to that, let's take a moment and talk about this bullshit. Template classes, this angle braces bullshit. You've seen it before. I mean, you've seen it with uniform int distribution when we're doing our random numbers. You've seen it with chrono duration. Even right here, you see it with numeric limits. So what the hell is this stuff anyways? Let's take a look. Take a look at our old friend dynamic int array. It walks and talks like your standard array. You can use square brackets to access, but we can specify its size dynamically at runtime, and all of the dynamic allocation and freeing, that's all handled automatically behind the scenes with our operators and our destructor, constructor, etc. And that's cool and all, but now say we don't want an array of ints. We want a dynamic array of floats. What are we going to do? Well, we can't store them in this thing. This thing stores things as ints. So, I mean, you could start from scratch and rewrite a class dynamic float array. But what you're probably going to do is copy and paste that shit, because you can realize that a dynamic float array, dynamic int array, they're almost going to be exactly the same, only a few changes. So this int pointer is going to be a float pointer, and these operators are going to return references to float. These news are going to create new dynamic arrays of float. And finally, we've got to rename this bullshit. And if you do that, if you jump through all those hoops, then you will have a dynamic float array. Not particularly hard, but a bit of a pain in the ass. Now imagine you having to do this for every different type of dynamic array you want to create. You could be doing this hundreds of times, and you're also duplicating a shit ton of code, because the code is almost identical, just a few things changed. This is bullshit. Enter the template. Templates basically allow us to do the copy and pasting bullshit I just showed you, but instead of us doing it manually, we make the compiler do it. We make the compiler do our shit for us, because the compiler is our bitch. So at the top of the class definition, you type template, and then you specify a template parameter that's going to control the templating of this class. So we're going to go type name, and we'll just say T. And so now T is going to be the thing that we can specify when we create a class using this template. And instead of having int pointer, we're going to have a T pointer. And now we're going to return reference to T. And now if we just go into here, we're going to be creating an array of T. And here as well, an array of T. So there we go. We've templated out our class. Now let's rename it, since it's now no longer a dynamic int array. It is just a dynamic array. Now if I want to create a dynamic array of ints, I just go dynamic array int DA1. And there you go. I've just created a dynamic array of ints. Oh, it's got to take a size, because we don't have a default constructor. So let's make a size of 5. And I could also make one for motherfucking floats. I just got to go dynamic array float. And I can make one for any type I want. I could make one for poo. I could make one for std string. It doesn't matter. And it will basically take whatever I put in here, and it will paste it everywhere you see a T in here, and make me a new class definition based on that. Let me put it another way. You remember the old analogy of classes being the cookie cutter and objects being the cookies? Well, let's add another layer to that. Template classes are like the mold that you pour molten metal into to make the cookie cutters. And the mold is adjustable. You can change some things about the mold to make cookie cutters, which are mostly similar to each other but vary in some respect. So the mold makes the cookie cutters makes the cookies, just like the template makes the classes, and the classes make the objects. Now take a look at this code here. We're creating 4 vector objects, and we can visualize the template and class instantiation as follows. So the compiler looks at our code and says, okay, you're using the vector template to create 3 different classes, vectors of ints, floats, and strings. So it's going to instantiate 3 class definitions: vector int, vector float, vector string. And then it's going to use those classes to create objects. Now, to the compiler, even though these classes are all related in that they were all generated from the std vector template, to the compiler, these classes are all completely different. They have no relation to each other. Now, at some point, you're probably going to want to create a function that takes a reference to a vector. You can't do this, right? Because vector by itself isn't a type name. That's just garbage. You have to specify what kind of vector it is. You've got to actually instantiate it. So here we specify vector of ints. Now this is a class type. Furthermore, like I said before, vector of ints to the compiler is completely different than vector of floats. They're incompatible. So you can't try to pass a vector of floats to a function that takes a vector of ints. That's not going to work, but if you put in there a vector of ints, that'll work fine. Keep those things in mind. Now, make no mistake, this stuff I showed you here with the template class, this isn't my attempt to teach you how to write your own template classes. This was just a simple crash course to give you an idea of what templates are and how they work. A more detailed tutorial about writing template classes will be coming in the future. We're going to be creating our own templates for our games, but for right now, I'm not going to teach that. I just wanted to give you a quick sneak peek to aid in comprehension. All right, so you've seen one way where vector is superior to our dynamic int array. We can use templates to make vectors that hold any kind of data type that we want. Let me show you another way in which it is superior. So we're going to get rid of this. We're going to default construct a vector. We're not going to ask the user for how many, and instead we're going to prompt the user to enter values. So we got here an infinite loop. We tell the user to enter a number. We put that into n. If n is less than 0, we break out of the loop. Otherwise, what we want to do is we want to put this number into our vector. Now, our vector, at the beginning, it has a size of 0, but we can grow vectors at runtime. So not only can we specify their initial size at runtime, but we can also grow them past that size dynamically. And the basic way of doing that is push back. So we can push a value back into the vector, and that will put it at the next available position. So if our vector right now has 0 elements, this will put an element at index 0. The next time we push, it'll push it into index 1, then 2, etc. And if we run this, we will get enter a number, and let's enter a few numbers, and we'll enter a negative number, and your vector contains 2, 3, 5, 6. Pretty sweet. Now let's take a look at some of the other basic functions of vectors. So, constructor. I've already shown you the constructors that we're going to need to know. You got the default constructor, you got the size constructor, you got the size and value, and you have the initializer list constructor. Destructor, self-explanatory. Equals, it just does a deep copy of the vector. I don't need to show you this guy. The assign function does the exact same thing. Now, get allocator. Anything to do with allocators, dead to us. Remember when I told you iterators are dead to us? Well, allocators are extra dead to us. Won't be talking about them. Forget about it. All right, let's move on. Element access. So you've got the index operator and you've got the member function at. They will both access an element. They'll return a reference to an element in the vector. The difference is that the index operator is not going to check the index to make sure it's valid, whereas at is actually going to check the index. Now, if the index is invalid with at, it's going to throw an exception. We're not going to be using at pretty much at all, and there are a bunch of reasons for this. First of all, I haven't taught you guys exceptions yet. Second of all, these kind of out-of-bounds errors should not be checked with exceptions. They should be checked with assertions. And third of all, it's slower to do all of your element accesses with bounds checking. So we're not going to do it, but it's there if you're interested. Member functions front and back will get you references to the first element in the vector and the last element in the vector. Especially back is useful. Sometimes we'll use it. Data, we'll get to this guy in a second. Iterators, dead to us. Forget about them. Capacity, empty, same deal as with your string. Actually, a lot of these guys are similar to string because they're both containers, right? So empty is going to return a bool. If it is empty, it's true. Size, we've already seen this guy, returns the size of the vector, how many elements are in the vector. Max size returns the max possible size of a vector container in your program running on the current system. I don't use it that often, but it's there. These guys here, reserve, capacity, shrink to fit, we're going to talk about them a little later in this video after I've introduced to you some ideas, so hold on to that thought. Moving on, modifiers. Clear clears the contents. Pretty simple, same as string. Now insert, in place, erase. These guys all work with iterators. So in string you were able to insert and erase and do stuff like that using indexes, but with a vector you've got to use iterators. So we're not going to deal with insert, in place, erase today, but we'll revisit these guys once we have learned about iterators. So for right now, these guys dead to us. Push back, you have seen it. In place back, I'll talk about this guy in a second. Pop back just removes the last element. Now this is different than the stack homework I gave you in that pop back for a vector doesn't return anything. It just removes the last element. So keep that in mind. Resize will resize the vector. Again, this is the same as string. You can specify count. You can also specify a value that will be copied if the size is greater than the current size. The new elements, you can give them a default value if you like. And swap just swaps two vectors. You got your comparisons. They will compare all elements in the vectors. swap, again, same thing as this guy pretty much, and that's it. Those are the basic member functions, except for a couple that I will deal with a little later on in this video. Now, vector functions, I'm gonna let you finish, but first I want to talk a little bit about how vectors actually work under the hood, their implementation. Alright, so since vectors are dynamic, you can probably understand that the memory for them, where the data is stored, is going to be on the heap. So you could imagine a vector implementation that looks a lot like our dynamic int array. You got a pointer that points to where the payload data is going to be stored on the heap, and you have an int that holds the size, how many elements are in the container. And this works. Now let's see what happens when we do a push back operation. So let's say we're going to push a value back into this thing. Well, obviously we can only hold 4 values in here. We're going to need a bigger allocation on the heap. So what you would do is you would allocate, let's say, an array on the heap, and it's going to have, 5 elements now. Then what you want to do is you want to copy the elements from the previous block of memory to the new block of memory. So you're going to copy all these guys in here, 42, 12, 18, 69. Then you're going to put the new value that you pushed in. Let's say you pushed in a big old 420 in there. And finally, you're going to, make this pointer point to your new block. And then you are going to erase your old block, and you are going to update your size. Now it's 5. So that could be how a pushback operation works. That's not how it's done in any vector implementation, though. And the reason why is, well, as you can see here, every time you push back now, you've got to do an allocation, which is expensive. You've got to deep copy every single element. Imagine your vector has 1,000,000 elements. You got to do 1,000,000 deep copy every time you add one element to the vector. That's absurdly expensive, right? So what it does instead is this. So it stores a pointer to the memory. It stores the number of elements that are being contained, and it stores a third value called capacity. That's going to be an int. And the way it works is when you push a value back, it's going to check the size and the capacity. It's going to see, is the capacity greater than the size? It is not greater. It is equal. So it is going to allocate a new memory block, but instead of allocating just the amount required, it is going to allocate a bunch of extra. You can see here it's doubled the size. Then it's going to do the deep copy. It's going to put the new element at the end here, retarget the pointer, and destroy the old memory. Now we want to update our values in here. Size is going to be 5, but capacity is going to be 8. And what happens now when we do another pushback? Well, if we do another pushback, we look at our capacity and our size. We see that we have extra capacity. So we don't have to reallocate. Now all we do is we create a new object, or we copy a value into the next unused spot, and we update the size. So by doing this, and by growing extra space, we reduce the amount of reallocations and the amount of deep copies that we need to do. And in general, the growth is going to be exponential. It might double every time, or it might grow by a different factor, but you're going to get exponential growth on your vectors. And if this looks a little familiar to you, you might recognize it from the SNEC game, because in SNEC, ahead of time we allocated a big array, but the segments we kept track of the part of the array that is used and the part of the array that is unused. And it's the same deal with vector. It keeps track of that shit. And for example, when you do a for each loop, a range-based for, it will only loop over the parts of the array that are used. It will ignore these ones. Now I'm going to prove to you that what I described is actually what's going on. So I created the class pube. It announces its construction and its destruction. And I create a vector of pubes, put 8 default constructed pubes in there to begin with. Now, pubes.capacity, the member function capacity, gives you the capacity I talked about. This capacity here, not the size of the actual used elements, but the entire capacity of the currently allocated memory block. So we're going to print out the capacity. We're going to try to push a pube back into the container, and then we're going to print the capacity out again. Let's see what we get. Run this. So, made a default pube, 8 times. That is just the constructor here, creating the vector and constructing 8 default pubes in the vector. Then 8 is the current capacity of the container. Make a default pube. This is constructing the temporary that we're going to push into. So we construct a pube, and we're going to pass that to push back. So we make a default pube. Now, copy a pube, copy a pube, copy a pube. This copying is happening because, remember, we have to take our old memory, copy it to the newly allocated one, and then we can destroy it. So this copy a pube stuff is for the reallocation. After these copies, we have to destroy all of the old pubes from the old block of memory before we can free that block of memory. So it does the deep copy, it does the destruction of the old block, then we get copied a pube. That is the pube that was being pushed in. So that's the 9th pube. Destroyed a pube. That is the destruction of this temporary pube. And finally, 12. So the new capacity is 12. So it didn't double. It increased its size by, basically its size went 1.5 times bigger. So apparently Visual Studio doesn't double every time, it goes 1.5 times bigger. At least from this simple test, that's what we can derive. It might be more complex, it might not be. But in any case, it's going to be exponential growth. All right, armed with this new knowledge of how vectors actually work, let's revisit the member functions and look at the ones I kind of glossed over a little bit. So, reserve storage. What this will do is this will increase the capacity if need be. So if your capacity is 12 and you call reserve with 20, it will reallocate and give you a memory block of 20. And this is very useful if you know how big your vector is going to be ahead of time and you want to push back into it. Instead of having that growth and reallocation and deep copy every time it reaches capacity, you can reserve the amount that you know you're going to need up front and then push into it without having to do any reallocations. Capacity, we've seen this already, returns the number of elements that can be held in the currently allocated storage. Now, shrink to fit. This will reallocate so that the capacity is equal to the size. And you might think, why do we need this? Well, resize changes the number of elements stored. So it will destroy if the new size is smaller than the current size. Let me just get you a picture here. So if you call resize and the size is larger, it will, insert new elements in the place and possibly reallocate. If you call resize and the size is smaller, it will destroy these elements, but it will not reallocate to make it smaller. It will leave the extra space as reserve space. So calling resize will not reduce the size that your container uses in general. So if you want to actually reduce the size that the container is using, you need to call shrink to fit. Now, a couple of quick tips about reserve and shrink to fit. First of all, reserve, if you know the size ahead of time, you might as well call reserve. You're not losing anything. But if you don't know the size ahead of time, if you've got to jump through hoops and twist yourself up to try to figure out the size ahead of time, then just let the fucker grow dynamically. Now, a shrink to fit, again, you can shrink to fit all the time. But generally I don't bother unless I really need to save that memory, or it's a really huge container and the extra would be a big waste. So I don't worry about it too much, but it's there if you want it. Now, the last of these modifier functions I'm going to talk about is InPlaceBack. It's very similar to pushback. It puts a new element into the next place in the vector container. But with pushback, let's take a look at it. As you noticed there, with pushback, you've got to create a temporary pube, pass it to the function, it gets copied, and then the temporary gets destroyed. That's wasteful. What InPlaceBack does is, instead of you having to pass in a pube that gets copied and then destroyed, you can construct the pube directly in the container. So you InPlace the pube. So with InPlaceBack, all you're doing is calling a constructor of pube to create that pube in the container. So let's get rid of this here. And we're going to call pubes with pushback. So that looks like this, and we run it, and we see made a default pube, copied a pube, destroyed a pube. So this made a default and destroyed, that was for the temporary, and the copy was for creating the pube in the vector. Now let's take a look at what it looks like when we do emplace back, and we're going to call the default constructor, so that's no parameters. And if we do that, we get made a default pube. So there's no need to construct a temporary, and there's no need to destroy the temporary. We can just create it directly in the vector, and that's a lot more efficient, obviously. And that is why, in general, with data types that have complex constructors, always use emplace back. Pretty much, you want to prefer emplace back to pushback. Now, for simple types like integer, it doesn't matter which one you use. So you can push back with an integer, you can emplace back. It's going to end up being the same code. But with something with a complex constructor, emplace is going to give you better bang for your buck. All right, let's introduce one last thing about vector. Now, let's say you've got a function. It takes just a pointer to an array of ints. So we can't pass vec to that function, right? I mean, if we try to do calc sum vec and then, vec dot size, obviously that's not going to work. Compiler's going to be, that's a vector. I want an int. What are you smoking, chili? Now you could try to, maybe I'll put the array of the vector, or the address of the vector, but that's not good either, because obviously the address of a vector is not the same as the address of an int. It's not going to make any goddamn sense. But there is one thing that we can rely on with vectors, and that is that the memory storage of a vector is guaranteed to be contiguous. So what that means is that the underlying array is basically like a C array allocated on the heap. It's the same idea. So what we could do is, for example, we could pass it the address of the first element of the vector, because this returns a reference to the first element. So we take the address of that. That's just an address of the first element, which is a pointer to this array. And so we could call, calc sum and pass it pointer to the first element, pass it the size of the vector, and it should give us the proper result. Let's go std cout, and we lost our shit because I fucking hate you. Calc sum, and yeah, this should give us the answer 6, and it does give us 6. So that's one way you could do it. You could also do it, address of vec dot front. Again, that gives you reference to the first element, and we'll do that, and it works. Again, result is 6. But here's what I'm going to tell you. The best way, the only way you should be doing this, if you want to get a pointer to the underlying data array, you should always call the member function data, and that's direct access to the underlying array, and it will return a pointer to the templated type. So if it's a vector of ints, it'll return pointer to int. This is how you should be accessing the underlying array. So in this case, we would just do vec.data like this, and it should give us identical results, and it in fact does. Now, you might have already been able to guess this, but for the homework, I'm going to get you to vectorify SNCC, because obviously it's a huge candidate for a vector instead of the bullshit that we have right now. So use vectors and practice your vectors, because vectors are arguably the most important container in C++ that you're going to learn, and you need to know them really goddamn well. That's it for today. Thanks for watching. I hope you enjoyed the video. If you did, please click the like button. It helps a lot. And I will see you soon with some more C++.